Today we are going to speak about rigid bodies. What is meant by a rigid body? So far we've considered bodies without any size, finite size or internal structure. We had to do mainly with mass points. That's of course an idealization. In nature you don't have true mass points, but bodies always have a finite size and are made of matter with a finite volume. A rigid body is a generalization of that concept. We move away from mass points and we look at bodies with a finite extension. However, you can at least at the beginning, you can imagine a rigid body to be composed of a collection of mass points. So a simple model that we are going to work with, at least at the beginning, is that we say we have n mass points. You can think of these maybe as atoms. So there can be very many. But for simplicity, at the beginning we say there's a finite number of mass points that make up a rigid body. The distances between these mass points are fixed. So this distance here, that distance, that one, and so on. All the distances that you can imagine, all pairwise distances between the rigid bodies, and so on, are fixed. This is what it is meant by the body being rigid. If you have, say, a droplet of water or some elastic substance, then of course by exerting pressure, by pushing on it, you can deform your body, and that changes the mutual distances of the atoms that compose that constitute the body. But this body here that we want to consider is rigid, so even if you push on it, you don't change the distances between the constituents, between the atoms, between these mass points. So this requirement that the body is fixed, that it is rigid, and that the distances are fixed, that imposes constraints on the system. It imposes constraints on the motion of the individual mass points. There is no internal motion, such as vibrations or deformations and so on. This is a rigid body. How many degrees of freedom does a rigid body have? First of all, how many degrees of freedom does a mass point have? A single mass point in three-dimensional space has 3 degrees of freedom. A rigid body with a finite extension has more than 3 degrees of freedom. But it also doesn't have, if the rigid body consists of n mass points, if the mass points were all independent, then you would have 3n degrees of freedom. But they are not independent because the distances, the mutual distances between the mass points are all fixed. So you have more than 3, but you have less than 3n. So how many do you actually have? Let's count. And I would like to show you 3 different ways how you can arrive at the number of degrees of freedom of a rigid body. Here's the argument number 1. Let's say you have a rigid body consisting of 3 mass points. So capital N is equal to 3. If the mass points were independent, if you had no constraints at all, then you would have 3n degrees of freedom, which in this case would be equal to 9. But then you have constraints. You have constraints on the mutual distances between the mass points. In the case of 3 mass points, these are in total 3 constraints. You have the distance between the first and the second body, between the first and the third, and between the second and the third. These are fixed. These are in total 3 constraints. So you subtract from the number of degrees of freedom that you would have without any constraints, you subtract the number of constraints, and the net number of degrees of freedom that you have is 6. Now you can sort of build your rigid body iteratively. You can start with the first 3 mass points, and then you add the 4th mass point, you add the 5th, and so on, until you arrive at the total number n of mass points. So let's see what happens with the degrees of freedom when you add to the 3 initial mass points, you add an additional mass point. We can iterate that procedure. So let's say we have I minus 1 mass points, and now we add the ith mass point. Then all the mutual distances are fixed as constraints. In particular, the distances of this ith mass point to the first mass point, its distance to the second mass point, and its distance to the third mass point are all fixed. And these are already 3 constraints. Now, already when you impose these 3 constraints, so I have 3 mass points distributed in space, and I bring in another mass point, and I fix all the distances to the given first 3 mass points, then already this specifies uniquely the position of your additional mass point. So already these constraints uniquely specify the position of the ith mass point. And therefore, associated with this additional mass point, there are no additional degrees of freedom. So in fact, the number of, after the first 3 mass points, the number of degrees of freedom doesn't increase anymore. And no matter how many mass points you have in total in your rigid body, the total number of degrees of freedom remains 6. This is one possible argument. I would like to show you a second argument which is even shorter. Consider your rigid body. This rigid body has a center of mass somewhere. Let me indicate with this blue dot the center of mass. And we can take the center of mass as the origin of some coordinate system. We can simply glue to the rigid body, we can glue a coordinate system with basis vectors, say E1, E2, and E3. So that's a coordinate system or a coordinate basis that is glued to the rigid body. And then clearly we can characterize the position and orientation of the rigid body by specifying the position of the center of mass and by specifying the orientation of this coordinate basis which is glued to the rigid body. So we say we characterize the rigid body by, first of all, the position of its center of mass, and secondly, the orientation of that frame, i.e. this basis, EI, that is glued to the rigid body. And let's count the number of degrees of freedom associated with these two kinds of data. We need 3 degrees of freedom to specify the position of the center of mass, and we need another 3 degrees of freedom to specify the orientation of the coordinate basis of the EIs. And again, in total, we arrive at 6 degrees of freedom. So again, also with this second argument, we find that a rigid body is characterized by 6 degrees of freedom. We will deal a lot with a special kind of rigid body, and that special kind of rigid body is called in English a top. In German that's Kreisel. In English it's a top. And a top is nothing but a rigid body which at a certain point is fixed in space. So there's you have a rigid body, and some point of that rigid body is fixed in space, and that is then called a top. This can be any point. Doesn't have to be necessarily the center of mass of the rigid body or any other special point, but it can be any point of the rigid body that is fixed. When you have a top, and hence one point is fixed, then the only kind of motion that you can have is rotation around this fixed point. So you no longer have translational degrees of freedom, you only have rotational degrees of freedom. And this implies for the number of degrees of freedom that then for a top you only have 3 degrees of freedom. Only the rotational degrees of freedom. So far this has been only terminology, more or less, aside from the counting of the degrees of freedom. Now we should proceed to describe the motion of such a rigid body mathematically. And 1 or 2 key concepts here are 2 kinds of frames in which we can describe the motion of a rigid body. The inertial frame and the so-called body-fixed frame. Implicitly, we already used the latter because the frame of which I said it's glued to the rigid body, that's a body-fixed frame. It's glued to the body. It rotates together with the body. Whereas the inertial frame, that is, well, when we are here in a lab, we perform an experiment, we have a rigid body rotating. Our rest frame, that's the inertial frame that does not rotate, and the body-fixed frame is glued to the body and it rotates with the body. So let me indicate here our rigid body. Then in the laboratory, we have the inertial frame, and I denote the basis vectors of the inertial frame by EI, E1 to 3. Then we have the frame that is glued to the rigid body at a certain point of the rigid body, which doesn't have to be the center of mass, can be any point. So let's say here, at this point, we glue a frame to the rigid body, and the basis vectors of that frame, let me denote these by EI primes. E123 primed. The origin of the body fixed frame is a certain distance d away from the origin of the inertial frame. And that distance vector I would like to denote by d. And then finally, let me pick an arbitrary point in the rigid body. Let's say we take this point here, point P. With respect to the inertial frame, this point P has position vector r, and with respect to the body fixed frame, it has position vector r prime. So these are the basic quantities, basic objects that we're going to deal with. To summarize, we have here two different frames. One is the inertial frame, abbreviation IF, inertial frame, with basis vectors EI. And then we have the body fixed frame, abbreviated BF, which I denote by EI prime. And the latter is co-rotating with the rigid body, and therefore obviously it's not an inertial frame. Now the fact that the body fixed frame rotates with respect to the inertial frame, we describe that mathematically by the fact that the basis vectors EI prime, they are not constant in time, they change in time. So their time derivative, EI prime dot, is different from 0. In fact, it's given by omega cross EI prime, where the vector omega is the vector of angular velocity. We already encountered this notion of angular velocity and that angular velocity vector, and also the concept of rotating frames at the very beginning of the semester when we talked about space and time and different reference frames. Here it's all coming back. Here you will see an application where we are going to need all that we discussed at the beginning of the semester. So omega, that's the angular velocity with which the body fixed frame rotates relative to the inertial frame. Now the angular velocity need not necessarily be constant. It doesn't have to be constant in time. If we look at the most general type of motion, the omega itself may be time dependent. So the omega may itself depend on time. Next, let us consider that point P that I indicated in the figure, that red point P. And let's look at the velocity of that point P as seen in the inertial frame versus the velocity of point P as seen in the body fixed frame. So we're interested in the velocity of point P in the inertial frame versus its velocity in the body fixed frame. And here we can go back to the results that we had obtained early on when we talked about different reference frames. I'd like to go back to the chapter on space and time, and here coordinate transformations. And there you see in the second red box in the middle, there's a formula for V primed. And that's the formula that describes how the velocity in one frame is related to the velocity in another frame. This is the formula that we are going to use. Let me try to capture that formula. So here it is. That is the formula for the velocity as seen in the body fixed frame related to the velocity v without the prime as seen in the inertial frame. Let's solve that equation for v, that is v prime plus d dot plus the sum over I xi prime ei prime dot. What is v prime? It's the velocity of the point P seen in the body fixed frame, so the frame that is glued to the rigid body. But in the body fixed frame, the point P doesn't move at all because the body is rigid. All the points stay at their position. So this is equal to 0 because the body is rigid. The ei prime dot, we said earlier that this equals angular velocity vector omega cross ei prime. But now this in turn, the sum over I xi prime ei prime, this is nothing but the position vector of point P. The xi primed are the components of the position vector of P in the body fixed frame, and then I multiply the components with the basis vectors of the body fixed frame, and I get the vector r primed. So at the end of the day, we can write v, the velocity of point P in the inertial frame, we can write that as d dot plus omega vector product with r prime. Let me give this equation a number 1, because we are going to need it later on. Let me dwell a bit more on the angular velocity vector. Now, that's the angular velocity with which the body fixed frame rotates with respect to the inertial frame. You may wonder if the angular velocity vector depends on the way in which the body fixed frame is glued to the rigid body. So you might wonder, if I take a different body fixed frame that has a slightly different origin and maybe a different orientation, then that will also rotate with respect to the inertial frame. The question is that rotation described by the same angular velocity vector? Or does the angular velocity perhaps depend on the choice of body fixed frame? Well, the answer is it doesn't, and here I would like to give a little argument why that is the case. So why, in fact, the angular velocity is universal in the sense that it does not depend on the precise choice of the body fixed frame. For the sake of the argument, let's choose a different body fixed frame, Bf prime, with now a different basis, which I denote by Ei double primed. So here's the picture from the previous page, and let's say we pick yet another point, this one here, and choose that as the origin of an alternative body fixed frame. And the alternative frame has also the basis vectors have a different orientation. Let's say they have this orientation. So this is E1 double primed, E2 double primed, and E3 double primed. The two body fixed frames, the original one, the green one, and the new one, the purple one, their origins are displaced by a vector which I would like to call little s. And the origin of the new body fixed frame, its displacement with respect to the origin of the inertial frame, is now no longer described by distance vector d, but by distance vector d prime. So here's another distance vector, which I call d primed. Now we can repeat exactly the same argument as on the previous page to relate to find an expression for the velocity of point P in the inertial frame. We can repeat exactly the same argument now for our alternative body fixed frame. And we find the same formula as before, only that we have d prime dot plus omega prime vector product with r double prime. Yeah, that is something that I have not denoted yet. The position vector of the point P in the alternative body fixed frame is now r double prime. Now let me see if I can still fit it in here. So this red vector here, this is r double primed. Yeah, so it's the position vector of point P in the body fixed frame BF primed, where we can express d primed in terms of the previous distance vector d and the vector s, which connects the two origins of the two different reference frames, body fixed frames. D primed is given by d plus s. So we have d dot plus s dot. We can also relate r double primed, so the position vector of point P in the new body fixed frame, we can relate that to r primed. That is the position vector with respect to the original body fixed frame, and that's given by r primed minus s. This implies that the formula for the velocity now reads d dot plus omega prime vector product with r prime, and then we have plus s dot minus omega prime vector product with s. Let me denote this equation by number 2. So we had on the previous page, we had an expression, a formula for v. That was formula number 1. And here we have an alternative formula for v. Of course, in both cases, we must obtain the same velocity of the point P, as seen in the inertial frame. So the two formulas, 1 and 2, they must agree. And this implies formula number 1 said that the velocity was given by d dot plus omega vector product with r prime. Formula number 2 says that the velocity is given by that formula here. So these two must be equal. You see that the d dot cancels out. And the important requirement here is that this equality must hold for any point P that I choose. And hence it must hold for arbitrary vectors r prime. So I can pick an arbitrary point P in the rigid body with position vector r primed in the original body fixed frame. And this equality must hold. So this must be true for any r primed. meaning for any point P. Well, for this equality to hold for arbitrary r primes, this is only possible, this is only guaranteed if omega equals omega primes and if this expression here is equal to 0. So we have two conclusions. The first conclusion is that omega primed must equal omega, and hence, as I had said at the beginning, the angular velocity vector that characterizes the motion of the alternative body fixed frame relative to the inertial frame is the same as the angular velocity vector for the original body fixed frame. Yeah? So in fact, the angular velocity is the same for all body fixed frames. And in this sense, it is universal. And the second conclusion is that the S dot is given by omega vector product with S. I'd like to introduce the notion of a reference point. That means the following. Let me make the usual drawing. So here we have the inertial frame, we have our rigid body, we have the body fixed frame. Now this is simply, at this point, just a terminology. The origin of the body fixed frame is called the reference point. Yeah? This is the so-called reference point. At this point, this is just a word, but I would like to make an assumption about the reference point. Up to here, the origin of the location of the origin of the body fixed frame was completely arbitrary. But now for the remainder of this chapter, I would like to make an assumption about the reference point. I want to assume that the reference point is either the point at which the rigid body is fixed if we are dealing with a top. I said earlier, a top is a rigid body with one point fixed in space around which it can rotate. If that is the case, if we're dealing with the top, then I want to assume that the reference point coincides with this point that is fixed. So either the reference point is equal to the point at which the rigid body is fixed. So if we are talking about a top, or else, if we don't have a top, but we have a rigid body freely floating around in space, then we choose the reference point always to be the center of mass of the rigid body. So this is an important assumption about the origin of the body fixed frame. So we now have two scenarios. One in which the rigid body is freely moving, and another in which it is fixed at a certain point, i.e. we are dealing with a top. Let me draw the rigid body, which somewhere has its center of mass, which I denote by C. In the first scenario, we just agreed that we would put the origin of the body fixed frame in the center of mass. Therefore, the reference point R equals the center of mass. In the second case, we have a certain point where the rigid body is fixed. this point need not coincide with the center of mass. Let's say it's this point here. This is the point where the body is fixed, and we agreed that this would then become the origin of the body fixed frame and therefore the reference point. As for the inertial frame, in the first case, the inertial frame is anywhere in space, whereas in the second case, I would like to make the additional assumption that the inertial frame has its origin also at the reference point, i.e. at the point where the rigid body is fixed. Let us next consider the angular momentum of the rigid body in the inertial frame. In our model, the rigid body consists of n mass points. Let me indicate the mass point nu somewhere here. Its position relative to the inertial frame is denoted by r nu. Likewise in the second scenario. From the general theory of the dynamics, the physics of n mass points that we had discussed in the context of Newtonian mechanics, we know the formula for the total angular momentum of n mass points. We sum over all the n mass points. We have the mass of the nth mass point, and then we multiply. We have the vector product of position with velocity. Or with respect to the body fixed frame, the mass point nu has position vector r nu primed, and as before, the position of the reference point, i.e. the origin of the body fixed frame, with respect to the inertial frame is denoted by d. We can now express r nu, the position in the inertial frame, in terms of r nu primed, the position in the body fixed frame. And we find that the total angular momentum then reads sum over nu from 1 to n, m nu, r nu, that equals r nu prime plus d, vector product with r nu prime dot plus d dot. This gives several contributions. First of all, we have the sum over nu, m nu, r nu prime, vector product r nu prime dot. Then we get a contribution sum over nu, m nu, d vector product d dot. And then we get the mixed terms. We have sum over nu, m nu, r nu, vector product with d dot, plus sum over nu, m nu, d vector product with r nu prime dot. Here is also unprimed. Now in both scenarios, these last two sums vanish. In the first scenario, the reference point coincides with the center of mass, and therefore the sum over nu, m nu, r nu primed is equal to 0. This is equal to 0 in the first scenario. In the second scenario, the origins of the inertial frame and of the body fixed frame coincide. They are both located in the reference point, and therefore the vector d equals 0. So, and also d dot equals 0. So this is 0 in the second scenario. And likewise in this term, here the sum over m nu r nu prime dot is equal to 0 in the first scenario, and d is equal to 0 in the second scenario. So to summarize, in both scenarios this is equal to 0, and we can neglect these two terms. As for the sum over m nu d vector product with d dot, in the second scenario this vanishes too, because again d and d dot are equal to 0. In the first scenario, d equals the position vector of the center of mass, and the sum over nu m nu, that is the total mass, and therefore this equals total mass times position of the center of mass, vector product with velocity of the center of mass in the first scenario, and this is 0 in the second scenario. In the first scenario, this can be regarded as the angular momentum associated with the motion in space of the center of mass. It is the angular momentum that the body would have if its entire mass was concentrated in a point at the location of the center of mass. And what remains is what is really the most interesting part of this angular momentum. That is the part that describes the angular momentum associated with the internal rotation of the rigid body, and this is the first term here, and this is the term that we are going to work with in the following. It is that contribution to the angular momentum which is due to the internal rotation of the rigid body.